So this week what we're doing in lab is looking at the process of when a solid dissolves and comes to equilibrium with the ions in solution. This is known as a solubility product. And the reaction that we'll be looking at is the dissolution or the dissolving of calcium iodate. So we have calcium iodate and we place it in water, and this begins to dissolve and forms calcium ions, and because of the 2-to-1 stoichiometry, 2 iodate ions. Now if you write the equilibrium constant for this reaction, you'll recognize that is products over reactants, except this is a solid, and because the calcium iodate is a solid, we leave it out of the equilibrium constant expression. So our goal, first goal in this experiment, actually is to just look at what this equilibrium constant is and measure it by actually measuring the concentration of iodate. Okay, so let's talk a little bit about how we're going to measure the iodate concentration. So we're going to take a 1 ml sample of calcium iodate, saturated calcium iodate, and we're just going to stick it in to an Erlenmeyer flask, and then we'll add some water to it. The exact amount of water is not important. Typically, we're going to add between 10 and 30 milliliters. The procedure probably calls for something like 25. Just try to be consistent with that number. Then what we're going to do is we're going to add Ki and HCl, and this is where the potassium iodide is important. This is where the HCl is important. And what ends up happening is this reaction begins immediately, and I2 begins to be formed in the solution. Now, if you remember from our previous experiment, that color of that solution would normally be a dark yellow or a brown. Now, there's enough iodate in this solution that it's going to turn brown. And then what we'll start doing is we'll start doing the titration. So we'll titrate with thiosulfate. And this is the tricky part of this titration. It needs to go fairly quickly, and you need to be constantly swirling it, because what it's going to do is it's going to turn to sort of a light yellow color. And then at that point, you're going to add an indicator to it, which is starch. Now, once the starch, I spelled start. All right, once you do the starch, then what ends up happening is it's going to turn to this sort of dark blue color, something like this. And then what you'll do is you'll continue to titrate it. Now, when you're at this light yellow color, let's talk a little bit about what that actually means. So when you get this light yellow color, this means the titration is almost complete. And that's because you've almost completely reacted all of the I2 that was created in the reaction with the Ki and hydrochloric acid. So you have to remember that when you continue the titration and you can titrate this with thiosulfate, okay, this is only going to, it's not going to take very much thiosulfate, and your endpoint will be a colorless solution. In a lot of ways, it'll look just like the first flask when you just added the water to it. It'll be colorless at that point. Okay, so we're looking for colorless endpoints. So this is the point where you have to be really careful with this titration. You don't want to over swirl it. You don't want to under swirl it. You want to swirl it really good and add a few drops at a time. The endpoints on this experiment are very difficult to get precise. Now, let me point out one other thing, and this actually complicates the whole process. While you're swirling it, this reaction takes place. And the oxygen comes from air. And what it does is it produces more I2. Since it's producing more I2, notice what that does in the reaction up here. It looks like if there's more I2 that there was more iodate. So you can actually swirl these solutions too much and you increase the volume that of thiosulfate that you'll need to get to the endpoint. And that'll overestimate the solubility of the calcium iodate because it looks like there's more iodate in solution. So while I say you want to swirl it, you also want to titrate very quickly. So once you get this first titration done, take a note of the volume, and when you repeat the second titration, just straight add in 90% of your titrant, your thiosulfate, and then swirl it one time, and you'll see it all react, and then go a little bit slower after that. That'll help to avoid the problem of getting too much titrant in because of the air oxidation of the iodide ion. So then what do you do with this number? Okay, so let me explain how you're going to use this number. So you're going to have a molarity of thiosulfate, we'll just call it MS2O3, 2 minus, like that, which is going to be about 0.010 molar. And the exact molarity, you need to check that on the day that we do the experiment because the thiosulfate is not super shelf stable, and so the technician will prepare it in the morning and then titrate it and figure out the exact concentration. So you need to check this value before you get started. And you'll write that number down in your notebook. All right, now you have to notice there's a couple of stoichiometries we have to use here. It's similar to the kinetics lab, but it's 2 moles of thiosulfate for every iodide, and then 3 moles of iodide up here for every 1 mole of iodate. Sorry, iodine to every mole of iodate. So when we're down here doing the analysis, the first thing you need to think about doing is getting the moles of thiosulfate in your experiment. And S2O3, right, 2 minus, that's just going to be the molarity and the volume. So you have a volume of S2O3, 2 minus, do it in milliliters, times the molarity of the S2O3, 2 minus, and that will give you the millimoles of thiosulfate. And then we have to do a couple of stoichiometries to get over to the millimoles of iodate. So what we'll do is we'll start with our millimoles of thiosulfate. And then we need to do our mole conversion. So the first reaction is this one. It's equation number 4. And it's 2 moles of S2O3, 2 minus for every 1 mole of I2. And then what you need to do, and I'll leave this part up to you, okay? You need to use the stoichiometry of iodine to iodate to finish this calculation. And this will give us, so this is from equation, sorry, let me go back, make sure I have the right equation. Equation number 3. Then we'll have millimoles of IO3 minus. Okay, so having done that, you need to have the molarity to do your calculation. So the molarity of, and I'm going to skip down to here because I'm going to use this space down here too. The molarity of IO3 minus is simply the millimoles of IO3 minus divided by the milliliters of solution containing iodate. Now, when you look at how we did the experiment, that's where you'll find the milliliters of IO3 minus, and that's this value. It's 1.00 mLs of saturated calcium iodate solution. So now that you have your molarity, your volume, you can calculate your molarity of iodate. Now, having said that, right, the millimoles is the molarity in this calculation. That's what it'll come out to be because of the 1 milliliter volume. So you'll get a number for that, and this is what you need to do. You'll set up an ice table that looks like this. So I have CaIO3, 2, in equilibrium with calcium ions and 2 iodate ions. This is a solid on the left, so we're ignoring it. So this is going to be my initial, my change in my equilibrium. Now, when we put the calcium iodate solid in solution, there was 0 calcium and 0 iodate in solution, but then it dissolved. So I got plus X plus 2X. And so this is just X and 2X. Now, this molarity is this value here, and I think you can see, right, once you figure out what X is, then you also have this value here. So your solubility product, your KSP, is equal to the concentration of calcium times the concentration of iodate squared, like that. All right, one last thing I want to say about this part of the experiment, because there's another part of the experiment, but one last thing I want to say about this part of the experiment is that X is also often referred to as S in these problems because it reflects something called the molar solubility. What does that sound like it means, right? It's just a molarity that will dissolve, right? So when you look at this reaction and you get a value for X here, it actually represents the moles of the solid that dissolve per liter. So that's what we call it, the molar solubility. It's the molarity that you'll get when you dissolve this substance in solution. Okay, so on to part 2. Part 2 of the experiment is done exactly the same way except this. So what we're going to do is you're going to get a 1 ml sample, right, of calcium iodate, but instead of being made up in pure water, right, it's going to be made up in a solution that was already 0.01 molar in iodate concentration. So think about what we're doing here. I'm going to go back down here. I have another ice table prepared. We ignore this because it's a solid. And we're dissolving calcium iodate in a solution that's already 0.010 molar. So as the calcium iodate begins to dissolve, there's still 0 calcium at the beginning. This will still be plus X, and this will be plus 2X, or 2S if you want to follow what's in the book. And then you'll have X, and you'll have 0.010 plus 2X. Now when you do the titration, it's done exactly the same way. It's just a sample that was prepared differently. You don't need to add any iodate to it that was already added. You're still going to go through this set of procedural steps. You're going to take a 1 ml sample. Now it's calcium iodate, but it contains some iodate already in the water. So that's why it's going to be labeled like it says here. It's going to be labeled, right, calcium iodate in 0.0100 molar iodate concentration. So back to the titration then. This sample is just different. You're still going to add the Ki and the HCl. You're still going to titrate with thiosulfate. Okay. It's still going to go to this light color, and then you're still going to add the indicator and turn it completely purple, and then you'll continue to or dark blue, and continue to titrate it until it's colorless. Now that volume will be larger than, or should be larger than, the volume that you used when there wasn't any iodate in solution. But here's what you'll find out, or hopefully find out. When you do this calculation, right, the molarity of iodate that you calculate, as we did for the previous sample, now is equal to 0.010 plus 2x. The value for x, right, you need to solve for. You're going to have to rearrange the equation. But the value for x, and this is called the molar solubility again, is lower for part 2 than for part 1. And that the reason is, and think about what this means. It means if you have one of the ions present in the solution, less of the solid can dissolve, because some of the ion is already present in the solution. Some of the iodate ion is already present in the solution. And we call this the common ion effect. So if we start dissolving a solid in a solution that already contains one of the ions, the amount of solid that can dissolve is going to be lower. Again, from the calculation, right, if you want to calculate the molar solubility from this data, it's still done the same way. It's still the concentration of calcium ion times the concentration of iodate ion squared. But now this is the iodate concentration, and you'll notice this. You'll have to solve this equation and plug it in for that value. And so it's not done. The calculation for part 2 is different than the calculation for part 1. So hopefully that sort of straightens out like what you're doing in the experiment a little bit. Of course, you can always ask questions, and if you have trouble with the calculations, review the video, but feel free to send text to me and ask me questions about how to get this done.